Hello, everyone. So happy New Year. My name is Weilong Chen from the USTC, and I'm a visiting PhD. And I'm a visiting PhD in the University of Houston. And today I will give a presentation about the AIGC tutorial. Actually, the AIGC contains two parts. The first one is a diffusion model, and the second one is a large language model. We call it like ChatGPT or ALLM. So, and today I only focus on this part, the diffusion model. As you can see, the diffusion model is very, very popular. You can see you can use a text to image to create very, very powerful image, and you can use like the inputting tools to if you want to bold, if you want to call on the bold, you can just do like the inputting, and also if you want to just create a feature like the pictures. You want to do an astronaut, you can just do like this. And also there are a lot of people do like this diffusion, a video diffusion model. You can see it's just like when you input this picture, input this video, it can diffusion to like this. So it's very, very impressive. Okay. So today I will this is outline. I will give some the update of the diffusion model from the DDPM to the latent constancy model, and I will also introduce some new list applications of the diffusion model. Also, I will teach you how can we use it, how can we just from the start and to the end, and we can train this diffusion model. First, let me introduce the overview of this diffusion model. Actually, in the imaging generation, we have a lot of tools like the GAN, VAE, flow-based models, and the diffusion models. What's the difference between the diffusion models and other models? Actually, the diffusion models, when they do the diffusion models, their size are always the same as the pictures. Unlike the GAN or VAE, they will do the encoder to a smaller size like Z. Z is different from X. But in the diffusion model, all the process like X1, X2 are their size are all are the same as X0. And the concept of the diffusion models is from this paper about 2015. Their motivation of this paper is like is estimating the small perturbations in the trajectory. Their essential idea is the first one is to slowly destroy the structure of the data, and through a interactive forward diffusion process, and then a revised diffusion process then restores the data structure. You can just see like this picture. This picture is like you put some dye into the water, and the water will be like the diffusion, and then the structure will be destroyed. And the core idea is we just do the recover the structure by reversing the time. And in 2021, the researchers from Bakery, they proposed the DDPM. And I think this is they demonstrate that the diffusion models are capable of generating high quality samples. And this is I think the very important research that put the diffusion models to a higher level. So let me imagine scenarios. Like the first one, if you want to model to generate some cyberpunk pictures. So firstly, you need to feed the model a set of cyberpunk pictures. Then tell the model, okay, you have to learn this data structure of the cyberpunk. So, and the model now they learn this the data structure of all the cyberpunk pictures, and the model can do like the generate the cyberpunk pictures. This is a core idea of the DDPM. So the essential role of the DDPM is to learn the distribution of the data. So actually the DDPM contains two progress. The first one is diffusion process. They will continually add some noises from the real picture and to the whole noise. And then the diffusion model will revise this noise from the real picture. We call it denoise process. We revise the pictures from noise step by step. And I will not give you some like the mass formulation. I will just do the high level to let you know what is the diffusion process. The first one is that, okay, so how can we add this noise to this picture? And everyone else, okay, we can just add a noise step by step. For each imaging, we can just add some Gaussian noise to the pictures and still until these pictures to the whole noise. But given the x0, how can we directly obtain the whole noise or each when you give a t, how can we get these pictures of the t? So here we use some like the reweight sampling. They do the mass formulation to get this like this one. You can get like the xt is equals to the like a weight or to multiply the x0 and plus epsilon. The epsilon we call it is a noise. So you can just remember about this formulation is okay. Xt can be directly obtained by the x0. And here is the denoise process. So what is the denoise process? It's like when you get a randomly noise of the picture, and the denoise process will from the randomly noise to the real picture. And how do we do it? It likes when we use this like the noise picture, then we will add it to our unit model. Unit model is a core model to predict the noise. When we predict the noise, and we will use this noise picture to minus the predict noise, and we get like a little real picture. And then again and again, every time the unit model will predict the noise, and the picture will minus the noise, and randomly you will get a real picture. And here is DDPM's algorithms. Like for the training, as you know, in this read box on the bottom, on the top, it's like the noise is sampled from at the test time, and this is our noise ground truth. And when we use this model to predict the noise, and it will calculate the loss from the noise and the predicted noise. What we do is to predict the every times noise. And do the sampling, we can just regard the sampling as a diffusion, as a revised process, and we also call it like a revised progress. And for this trained model, they start from t to 1, and they will gradually remove this noise according to this formulation. So this is all the DDPM's formulation. You can just understand it from a very high level. And this is a core model structure of the DDPM. And also this unit is also a very key model structure for the whole diffusion model in our researchers. A unit actually contains two parts. The first part is the encoder, and the second part is decoder. For the encoder, the picture will send to the encoder, and gradually to do we call it like a downsample block. It will downsample this picture, and to like this, we will put this the whole real imaging to an embedding. The embedding we call it like a middle block. And the middle block will be the up sample block, and we'll get a real picture of this decoder from this decoder. Sorry. Yes.
You mentioned that the difference between diffusion model and other different kind of generated AI model is that the diffusion model they they use the same picture size or data size during the whole process. So why there is a encoder and decoder here? So,
Oh, it is because it is just the model to predict the picture. So the encoder and decoder is try to enhance the model to learn this distribution. It's not for like yes. Mm-hmm. And here we also introduce the DDIM. What is the difference between the DDPM and DDIM? As you can see, for the DDPM, when you do the revised process, you have to do the step by step from the 100 and to 1. You cannot skip any. You cannot skip when you do revising. But the DDIM, it can do revise. It can do the skip diffusion process. You can see from the 100 to the 0, it can skip from like 20 steps. You can skip. So for the DDIM and DDPM, DDIM can do like faster, maybe five faster than the DDPM. So when we introduce the base concept of the diffusion model, I will introduce some open AIs. They also introduce some very new diffusion model. So this work named diffusion models begins on the imaging system thesis. Okay, I don't know how to say this word. They improve synthesis. Okay, in this work. This is the first time that diffusion model beats the GANs. They win the GANs on the FID. They win a lot of metrics on the GANs. So what they do? The first one is they improve the unit. As we can see, when we see the unit, it's an encoder and decoder, but actually there are a lot of very details in this unit. Like, okay, there are a lot of attention machinism, and there are a lot of attention hits, and there are a lot of like the upsampling block with some residential block. So in this work, they improve it from the they add more attention. They use a big gain residential block, and they also try to increase the dips, and reduce the width into the model, and try to make the model size the same. And actually, we can see this table. They really do some progressive of the unit. And here is also I think a good improvement of the diffusion model. They propose a classifier guide. So what is classifier guide? Imagine if you want the diffusion model to generate a dog. So what can you do? You have to feed a lot of dog pictures to this model, right? So if you want to generate a cat, so you have to feed a lot of like pictures like the cat. But when you feed a lot of cats and dogs pictures to the one diffusion model, what can you do? What will it generate? So you cannot know what will be generated. So in this model, they train a classifier to identify what this picture is. Like, okay, this picture is cat. So they train another model like a classifier, and they identify, okay, this picture is a cat, and this picture is a dog. And when they do the sampling, they will use this classifier to guide this diffusion, to guide this generated progress. Okay, what they do is when they do the sampling, like when they do the revised process, they will end like this formulation. They will end like the classifier, the gradient of the classifiers into the sampling, and they will guide, okay, when I think I need to generate a dog, so I will put this dog's gradient to this sampling process, and then the model will gradually generate a dog. So this is we call a classifier guide. But actually, when when you see like this formulation actually there are a lot of math formulas behind this formulation. So I did not mention about that. You can just understand it from the high level. And the guide from the OpenAI, they also do some like the classifier free guide. So as you can see, when we see like you have to generate a cat pictures, or you have to generate a dog pictures. This category have to be in your data set. Okay, the classifier you train, okay, you only contains dogs and cats. So you cannot generate other like you just want to generate mountains, you can just generate humans. But when the classifier do not have the data set, you don't have the human, do not have the mountain. So the classifier guide cannot do like this. You cannot generate like the mountains or humans. But the classifier free guide can do this. So what the classifier free guide is do, like the free, you can see the free, it do not need a classifier. It only use some like the text captions, or just they do not need the directions. They just do like the, okay, during the sampling, they can just they generate some text prompts, and then sometimes replace the text captions with the empty sequence during the training, and they try to pull this model away from the empty sequence, so they can gradually generate the pictures closer to the text or closer to the directions. So this we call the classifier free guide. And they also proposed a clip guide. So what is clip? You can just see, okay, the clip contains two parts. The first part is an imaging encoder, and second part is a text encoder. When people input the text and imaging to the two encoders, if the text and the images are closer, they will get a very close. When they do the multiply from the two encoders, they will get a very high score. If the text and the imaging are far away from each other, they will get a low score. So as you can see, we regarding the FX as a imaging encoder and the caption and the GC as a caption encoder. So if the caption and the images are close, so the FX plus GC will be large. Otherwise, it will be low. So as you can see, if the XT are more like the captions you give it as a C, it will get a higher score. Or just you can see just have a large update. Otherwise, it will almost do nothing. So between the classifier guidance and the classifier free guidance, there are some difference between these two. For the classifier guidance, okay, you do not retrain this model. You just need to train a classifier model. Like you have to train this picture from like the dog or like the cat. But the classifier free guidance, as what we mentioned about the grid, so they have to totally retrain this model, because you have see like during this training, you have to use this epsilon and to try to modify the whole model structure. Sorry, you might modify the whole model update. So, but and the classifier guidance, you need to train a classifier model, but classifier free guidance, sometimes they just use a pre-trained clip model. And here, classifier guidance, they can only control the category in the classifier model. But the classifier free guidance, they can do any conditions. You can input some text into the model, and you can generate anything. So in nowadays, so people always like to use the classifier free guidance. And here is I think it's a more newer method from the OpenAI. They proposed the DALL-E 2. what the DALI2? Actually, the DALI2 contains 3 parts. The first part is a clean model, as what I mentioned. The clean model actually has they train a text encoder and the image encoder. You can see like this. Okay, when they input these pictures like the dog, and they will do they will also input a text like the corgi playing a frame throwing trumped. So and they try to train it to make this text encoder and the image encoder to get close. And then the step 2 is to train the prior. So what is the prior? They try to make this output of the text encoder to try to make the text representations more closer to the image representations. What they do, they use a diffusion model to make it closer. And when they do that, finish the imaging, when they finish training the prior, and they will use a decoder from this. You can see from this imaging representation to a real picture by using this decoder. So this is the whole DALI. This is the whole DALI model structure. So what is the why it is so efficient? I think maybe they use a large clip model. They use a large diffusion model in the prior, so they can do like a very, very impressive results. And here we will introduce like some latent diffusion models and latent constancy models. Why we mention it is because I think it's more closer to our communication area. It's because when you use the latent constancy model, you can just do the diffusion model in maybe 0.1 seconds to generate a picture. You see, when you do like the DDPM or DDIM, you have to like 20 seconds. But when you do the latent constancy model, you can do like very, very few seconds. So let me introduce the first thing, the latent diffusion models. I think the latent diffusion model is also very impressive. It is the base of the stable diffusion models. So what is the latent diffusion models? It actually, you can see from the pink box, as we can see, the diffusion models, when they do the diffusion, their size are the same as the real picture. But in these latent diffusion models, they try to make the real pictures to make a smaller size of the original picture. Like from the X, when they do like a model into a Z is small than the real pictures. And they use this Z to do the diffusion process and do the denoising process. So it can very, very lower the computational demand for the training diffusion models. And I think what we can learn from this is that we can also, maybe when your representations is very high, or you have a large representations, and you can do the VAE to get to a smaller size, and you can do the training. And what's more, they also, as you can see, what we do in the classifier guide or classifier free guide, they use like the text, they use like a classifier to train this model and to guide the diffusion, to guide the denoise process. But in this work, they try to put the condition, like we take representations and images to the tau theta, and to make this tau theta into the denoising unit process. They multiply to the QKV and to try to control this this unit to get a more better pictures as you do the condition, you do the text representations. And here we will introduce the constancy model. So what is a constancy model? As you can see, the constancy model ends a new constraint that every picture from the diffusion process, it can use a f theta to get the origin pictures. Every step, you can see, okay, when we do like the step for 100 pick 100 time steps, and the picture will, you can also still use the f theta to, from this picture, get directly back to the data. So what can you imagine that, okay, when I use this noise, maybe we can just directly use the f theta to get the original data. So you do not need a long denoising process. You only maybe need only once. So the constantly model define a constantly function. The constantly function contains two features, like the f x epsilon is equals to the x. You can just see, okay, to the x0, you can just when you do like the f theta, like this, like in this picture, you can also get this original picture. The second one is, okay, when you do like the f theta, and you can at any times at any time steps, you can change the steps, but they are outputs of the function are all the same. So to try to make these two features come true, okay, the constancy model, they propose two steps. The first step is to try to meet the first one, the first formulation. They do like they were recording the second research. They define the f theta to like this formulation. And the step 2 is to end the constancy distillation loss. So what is a constancy distillation loss? It actually to use okay, what you can see is the f theta. F theta is what we define the we catch f theta. Okay, what we define is this function. Okay, we try to make this function is try to make them closer to the xtn from the xtn plus 1. So what they do is try to, okay, if you like the t maybe 100, I try to make the 100 time step the pictures are closer to the maybe 1000 pictures by the f theta, and then they end this constraint to the while they are training the diffusion model. So that's the constancy model. And what can they do while during the sampling? So what they can do is to, okay, now we have a noise picture at this point, okay, and this point will do the f theta. Okay, you can get the f theta to back to the data. Okay, when they back to the data, they will continually end the noise at like time step t1. Okay, then they get at this point. And at this point, they will still to use this f theta and to get this data. You can see from this line. Oh, sorry, from this line. Okay, they get our original data. Then they end noise, and then they will do like the loop. So during a multi-step sampling, they will get a better feature. They will get a better picture. So this is a constancy model. And here we will introduce the, I think maybe very, very new model, like we call it a latent constancy model. So what is a latent constancy model different from the constancy model? It's they end a latent VAE, as we can imagine that the VAE put the real picture to the Z, to a smaller size of the pictures. And they also use a guidance scale. The guidance scale, you can see just like when we do the classifier guidance, we have to, or when we do the classifier free guidance, we have a scale that identify whether how strong the guidance will guide us. And also we will do the diffusion skip number. It determines how can we escape this number. And in the latent constancy model training process, the step 1 is to, okay, we sample some data, Z is a picture and C is a text. And we choose N as a diffusion time step, okay. And the W is as a scale of the guidance. And step 2, we do the diffusion. We can get the picture, the noise picture at the Z N plus K. And the step 3, we will do the denoise with a DDIM diffusion scheduler or some like a DPM solver. And the step 4, we just try to compute the constancy loss based on the Zn plus K and Zn. You can see this constancy loss is what we mentioned. We try to make the Zn plus K and Zn from the F theta are the same. And step 5, we do the upgrade model, and step 6, we will do the EMA. Actually, EMA is very a very good tools in the diffusion in the deep learning ways. You know, deep learning models, they can try to make average of the parameters, and we'll get a more stable models. So as we can see, the latent constancy model, they will only use maybe 2 steps or 1 step to generate very, very good pictures. Okay, after we discuss all the base diffusion models, I will try to give you some about tools to train or to use these diffusion models. Actually, we use the diffusers. So what is the diffusers? The diffusers is from Hugging Face. They build a lot of diffusion models in their website, and if you want to use some models, or if you want open source code, you can just from the diffusers you can get this code, like this one. If you want to use the DDPM, you can just from diffusers to import the DDPM pipeline and do like you from pre-train you can get the model that other have trained trained, and you can just from the pre-train and get the images. And for using like the LDM, like the latent constancy model, so you can just use like this to do the pipeline and from pre-train and do like the images to use some prompt into the model, and you can just do the image, you do the generation. So if you want to train your own diffusion models, what you can do? So actually, diffusion models have a lot of training ways. Like you want to just train like the DDPM or DDIM. You know, you do not need any conditions. You do not need any text or other images. You can just need some pictures. As you can see, you can maybe just butterfly, the pictures of just butterfly. But you want to use some text to imagine or imagine to text or something like this things. You can just make a text imagine pair like this. Okay, we saw the Pokemon pictures and the description of this imagine. So let's first introduce the DDPM, the process of DDPM. So the DDPM is just okay. You only need the pictures like this, all these pictures, and then you will do the train data loader to try to make it into a PyTorch data loader. And then you have to define a model, a unit model, as you can see in this code. You can define the model. You can use a block out channels. You can define the up block types and down block types. They can always be like very simple. Use some text to create this unit model, and then you have to define a DDPM scheduler. So what is a DDPM scheduler? This scheduler is for ending some noise to the original pictures. If you input a time step t and you input this image, it will end the noise like this. I end some like the time step about 1000, and you will get a totally noise pictures. And then you can define this training. So what is the training? What you have to define that. First you have to do like the common PyTorch training ways, and then you have to define a time step that you have to choose, like any random time step, and then you have to add some noise to these pictures by your random sample time steps, and then you can just do the model predict, and you can get the noise from the model predict, and then it's a loop. So you continually training this process, and you can get these pictures. And the step 5 is to define the evaluate. So what is a define? What is the how can we define this evaluate? It's also very simple. When you train this your model will be saved on the space, and you can read the space name from to input this from pre-trained functions, and you can directly use your DDPM models, and you can just do okay. Like the first one, okay, you load these models, and the second one you do like the noise processing, and you can get a picture. This is what I train the butterfly model. And if you want to train by yourself, you can just to do this official guidance from the Hugging Face. You can directly to use this website, to use this link. And we also introduce another type of the training, and we call it text to imaging. So what is text to imaging? Is that okay? You just put some text, you use some text, and the model will get your text and generate some like the pictures from your text. So actually, text to imaging is very hard to train. You have to use like a very many GPUs. So actually, people would like to choose a base model that the people have the big company has trained, like the stable diffusion models, like other models, and then when they will load their model like this place. As we can see from the latent diffusion models, so we count in 4 parts. The first part is the VAE model. They will pull this original feature to a smaller size, so we call VAE. And the second one is a noise scheduler. It's the diffusion process. It will end noise. And the second one is a text encoder, like this one. You will do the conditional and try to make this text representations to the tau theta. And the third one is this UNet. They will to predict the noise from the pictures, and they will know the UNet from the other models. So you can just try to define these models. And what I want to introduce to you is we call it the LoRa training. So what is LoRa? As you can see, as I have seen that the big companies, they have a lot of resources, so they will use a very large models. But actually, in our own computers, we do not have a large models. We do not have a large GPU. So what we need to do is to use a LoRa. So I will introduce what is a LoRa. Actually, as you can see, the pre-trained weights is a big weights. But when we do like the separated, we just try to put we just separated from the W to A and B. You can see the B, if the size of the B is a D multiply R, and the A is R multiply K. When they do the multiply, they will get a D plus a D multiply K, and the size is almost the same as a pre-trained weights. So when separated from the W0, we can just get a smaller size of the parameters B and A. And we also find that, okay, so what is R? The R is actually the when you do the A and B, you can see how can we put it small. R can be like 1, 2, 3, and you can get a very smaller small weights. And actually, what you can do to train the LoRa is very simple. Okay, you can use this LoRa config. Okay, you define the R, and you define the rank. You define what the initial you use to initial the A and B, and you can define what the target models. So what the target models is actually the how do you want to what is the W? The W is like when you do the diffusion models, there are some UNets, right? UNets contains like the transformer, like a lot of QKV. So in this, you can just try to modify. Okay, I only need like the KQV in the self-attention. And other ways I do not need. So target model is defining what your LoRa want to train. And step 4 is to define the text tokenizer. Okay, if you are an peer, you may know what is the text tokenizer. You try to make the text, like the English alpha to ID, like okay, A maybe equals to 1, and the 1 can be understood by the computer. Okay, and the step 5 is to train this model. So how to train this model, I will also introduce this type. Like the first one, as we can see from the above pictures, it will do from the real pictures to latent to the Z. It's to use a VAE encoder. So you can get latency. The latency is the Z. And then you will continue to do other steps just as other diffusion models do. Random time step and noise. And the third one is you have to put your text into the representation, like embedding, okay, at the tau theta. And then you will use the model predict to combine the text representation and the latent representation. And then the unit will give you a model predict. And then this is a loop, continuing loop. And so and the final step is to, okay, you have trained your model and you want to load this model. Okay, you can just do this pipeline. You can from pre-train to get this model and load this unit and the LoRa ways that you train and just do the text to imaging. As what I do is to do some prompt like a Pokemon with green eyes and red legs. You can see we get the picture. Maybe it's not a red legs, but I think it's close to. It's only because I only train about 10 epochs, so it's not a very good model. But I think you can just use this. And actually, you have a lot of training ways, like you can use text to imaging, the unconditional imaging generation. The unconditional imaging generation is like a DDPM. You do not need any text guide or just like the classifier guide. And the text to imaging is what I show you. Just put some text to the imaging. And the text inversion and dream boost I will introduce later. And the control net, actually the control net is that you want to put some images like what we see on the first page. A man is just like dancing, and in the video, all the cartoon the cartoon characteristics, they also do like the same as a man who is dancing. So it's like more like a control net. And other training ways you can just explore by yourself. I think they are all very interesting. And now I will introduce you some the newest applications of the diffusion model. As well as we can see the textual inversion. Actually, this is also very funny tools. You can see from the left pictures, you input some pictures of okay, we just call it S. Okay, then when you do the diffusion models, it can, okay, we want to do the oil painting of the S. Okay, you will generate the painting of the S, and like the emo sitting in the same pose as S, it also do like this. So it can generate specific concepts like the personal objects and article styles, and try to describe them in using a new words into the pre-trained text to imaging models. And what the same as what I mentioned is a dream boost. Dream boost is actually the almost I think almost the same as a previous one, but they use different training ways. They also input some pictures and try to get some subject of the whole pictures, the same subject of the whole pictures, and they will pull these pictures into the other text prompt, and they will pull this subject into the pictures. But actually, I tried. I try to use my pictures into this, but it cannot be worked because I think maybe the human face is very difficult to identify. But the dogs, like these dogs, actually they have been trained a lot of times during the pre-trained model, so they can identify this. But when I put my face on the Dreamballs, it cannot work. And the LoRa, what I mentioned, the training ways, it can reduce very, very big from your limited resource. You can train your model on the resource. Yeah. And I also want to introduce your very, very newest how do you say, the GitHub repo. You can see the diffusion model do not need any how do you say, latency. Yeah, you can see this is the pictures, this is the real pictures, and this is the diffusion pictures. It has almost no latency. And you can see about this one, the FPS can almost equals to 100. So it's like a very, very fast diffusion process. So I think maybe we can use these things to do a lot of communication process, or just try to use like these things. And I also want to introduce the video diffusion models. Video diffusion models actually the newest tools in the diffusion process. Oh, sorry, diffusion models research area. So they will try to use some text or try to use some pictures to generate how to say, move picture, or just like a movie. And the PIA also is a personalized imaging animation. You can put the pictures into a real, how do you say, a real a movie, like the pictures, the GIF. And when you do the boy is crying, okay, they are really crying. And when they do smiling, okay, this boy is smiling. And actually, I also try to do the Pika. The Pika, maybe you have heard a lot of things about Pika. The Pika is also a video diffusion model. When I input our group meeting pictures to the Pika, I say, okay, could you please help me to write? Could you please help me to generate like a group? We are doing the group meeting with a bumper soccer. How do you say, bumper? Okay, and they give me this like this. Okay, you can see. Okay, I think it's nonsense. I don't know why. It's like it's like the ball is blooming. I don't know, but actually when I input this picture, the prompt is like, okay, I want to have, could you please show me like the firewall of the Houston skyline? And it input like this. I'm not sure if these buildings you are familiar with Houston. Okay, but it is a real impressive, right? Okay, okay, and that's all about my AIGC tutorial. So thank you. So any questions?